Swayam Prabha. Digital India. Educated India.
So X1 and X2, and then H11, H12 are the two hidden layer neurons. H21, H22 are the hidden layer neurons in the next layer. So this is the notation also. Uh, the H11, H12 indicates first neuron and second neuron in the first hidden layer, and H stands for hidden. H21, H22 would be first and second hidden layer. The values are also accordingly decided. So W11, 1, we know that the index close to the symbol is the destination neuron, and index the other index is the source neurons index. So W11, 1 is the weight which is from X1 to H11. Similarly, W12, 1 is weight from X1 to hidden neuron H12. Similarly, if I go from hidden layer to hidden layer, then these two weights from H12 to H22 is W22, 12, 22 destination, 12 source. Then W21, 12, 21 destination, 12 is the source. And finally, W22, 22 is the weight to output neuron O2 from hidden neuron 22. Okay, so this is the notation, and this is what we follow in our discussions. Now, this is a network which is, of course, artificial, but um, not really uncommon. And in fact, this is the structure which comes when we make use of recurrent neural networks. Okay, recurrent neural network is feed-forward network folding in unfolding in time. So the neural network goes on adding components on its stack in a time step manner. So this is a feed-forward network, and we want to understand what is the operation and the vanishing exploding gradient problem. So let's go slowly and carefully over it. So X1 and X2, when they are presented as input, the somebody has to mute your mic, please. Everybody, please mute your mic. Okay. Uh, so H11, H12 would receive the inputs X1 and X2 multiplied by the weight values on the connections. Similarly, they will send forth activation to H21 and H22. From H21 and H2 to O1, O2. Everywhere, the inputs will get multiplied by the corresponding weights on the connection, and what arrives at any neuron is the weighted sum of the activations from the previous layer. Now, once the activation has reached the output layer, we are able to compute the error and the delta value. So delta value is nothing but the difference between target and observed at the output layer multiplied by gradient, note the term gradient, or the derivative of the input output function at a neuron. And this is further generalized to say that the delta value at any neuron is a gradient of error with respect to the net input at that neuron multiplied by derivative of the input output function. Okay, at any neuron, this is something called the delta value. Delta value is derivative of the error, okay, with respect to the parameter multiplied by the derivative of the input output function. So here this turns out to be equal to target minus output, okay, at the final layer neuron. The delta value is target minus output into derivative of the sigmoid. And derivative of sigmoid is not really sacrosanct. Whatever is the input output value, radial basis function, ReLU, anything, that would be the delta value here. So delta at O1 is equal to T minus O1, T1 minus O1 into derivative of the sigmoid at O1 or the input output at O1. So now this gets back propagated, you see, this gets back propagated. So the delta value here will be equal to delta into this weight W2, W21 plus delta value here into W1, 21. Okay, so delta at H21 is delta into W2, 21, delta O2 into W2, 21, and delta O1 into delta W1, 21. Okay, so from there again, similarly this way we can find delta value computation stops. And each delta is recursively computed, as you know. Okay, the delta here, for example, in H11 is nothing but delta H22 and delta H21 multiplied by the corresponding weights. This is why it is called back propagation. The weights are W2112, W2111. Okay, so I can begin looking at delta X1 now. Okay, delta X1, because delta X1 is like the root of a tree. So delta X1 depends on delta H12, delta H11, delta H11, delta H12. Delta H11 depends on delta H21, okay, and delta H22. Delta H12 also delta H12 also depends on delta H1, delta H21 and delta H22. Okay, and delta H21 depends on delta H21 depends on delta O1, delta O2. Okay, delta 22 depends on delta O1, delta O2. Okay, so this same tree delta O1, delta O2 is replicated 4 times for each of these delta H21, delta H22, which again are replicated 2 times for the children of delta X1. And you can see the tree. Okay, why is it a tree? It depends on the hidden layers, deltas. The hidden layers deltas depend on uh, upper hidden layers delta. Upper hidden layers deltas depend on the deltas in the output layer. And you can see that as the number of hidden layer neurons increase, the number of layers increase, this tree will go on uh, expanded, okay, to lower and lower levels. And we can do some combinatorics and see how the terms expand out. So delta x1 is multiplied by weight and delta h11, weight and delta h12. Delta h11 is delta h21, delta h22 multiplied by weights plus delta h12 is delta h21, delta h22 multiplied by weights. And these expressions are again multiplied by W112 and W111. Okay, so if you expand it out, first of all, uh, delta x1 will consist of multiplication of weight and another delta term. So delta x1 will consist of addition of 2 terms, delta h1, and each of these addition terms is product of 2 weights and a delta value. Okay, so product of 2 weights and a delta value. In the next level, we'll have uh, 8 terms, 2 to the power 3, 8 addition terms, and each term will be containing a delta value multiplied by 3 weight terms. Okay, 3 weight terms. So this is the way the number of terms will increase exponentially with the number of levels. Okay, and each term will have order of L terms. So this is what is written here with B as the branching factor and L as the number of levels. There will be B to the power L terms in the final expansion of delta x1. Also, each term will be product of L weights. Okay, is this clear to you? So the final expansion of delta x1, where the recursion will stop and it will have only the delta value of the output neurons, which will be expressed in terms of uh, target and observation, target minus observation. No more recursion, no more recursion. So at that point of time, at that step of expansion, delta x1 will have b to the power L terms, where b is the branching factor, b to the power L terms, and each term will have L weights multiplied by a delta value. That delta value will become the final boundary condition for t minus o multiplied by the derivative of the neurons input output. So you can see that there is an exponential computation involved as the number of layers go on increasing. Okay, so let's understand this phenomenon. Okay, so as the number of number of hidden layers grows, and as the number of neurons in the hidden layer grows, the number of parameters also become very large. In particular, the delta value, which is a function of the gradient, that will have b to the power L terms, and each term has L weight values. Okay. Now let us have a uh, back of hand calculation. Suppose there are 10 neurons in each hidden layer, and there are 10 layers. 10 layers is a large number of layers, but absolutely not unheard of in today's large neural network based computation. Okay, GPT-3, for example, apparently has billions of parameters. How can billion come? Easy. You see, if there are 10 neurons in one layer and 10 to the power, and there are 10 hidden layers, each containing 10 neurons, b to the power L is 10 to the power 10, which is 1 billion terms. 1 billion terms for delta x1. To get delta x1, I will have to have 1 billion terms addition. Okay, and each term will have 10 weights multiplying a delta value. So this is now the source of vanishing or exploding gradient. Now you see, if each of these terms are positive in the exponential expression for delta x1, if each of these terms are positive, then you have addition of b to the power L terms, which itself is a very large quantity. So that is an exploding gradient. And you don't have to go so far. If L terms, let's say 10 weight terms are multiplying each other, that itself will be a very large number if all the weight values are above 1. If the weight values are between 0 and 1, can explode or vanish. Okay, even at this at lower layers of computation also. I mean, you start with O1 and O2 and keep on computing deltas. Very soon you will have large number of terms, and each term with large number of weight values. So that will give rise to underflow, overflow, etc. And that is the vanishing exploding gradient problem. You may say that if the product of terms is, if each weight value is between 0 and 1, and if the product of terms is taken, that will be a very small number. But if I add them together, then the number will be large because there are exponential number of weight values. Now the weight values you do not have much control on. They can be negative, they can be fraction, they can be positive, more than 1, and so on. But in the worst case, you can have this kind of uh, very small and very large values, which are which put the computation in difficulty, and you will have to arrange for some engineering solution to this, and that is to this problem, and that is what is done in the long and short term memory. So LSTM has a kind of window, okay, window for cutting out the computation after a certain level. So I go on computing delta x1, but as I go lower and lower, I do find that the new terms are not contributing anything, okay, because suppose they have become very small, then I'll neglect them. And if it is an exploding gradient situation, then also I can think of a solution to cut out computation. Okay, so this is the vanishing exploding gradient problem, which can be understood in terms of an exponential tree rooted at delta x1 or delta x2, which are neurons at the input layer. Okay, and order of b to the power L terms in the final expression, where L is number of levels and b is the branching factor. So anyway, this kind of discussion, with an exponential tree, etc., you probably cannot find in textbooks or papers. So these slides should be important for you. Another very important point we discuss is called the symmetry breaking problem. Uh, we start with XOR and we find, suppose we decide that all our initial weights will be same. Okay, normally the weight values are randomly initialized and they give rise to different values. Now I decide that, well, I'll have all values as 0, let's say, or all values as 1. Then what will happen? This network is adequate for XOR. Okay, this is the right architecture for XOR. There are two hidden neurons who will compute x1, x2 bar, x1 bar, x2, or will compute NAND and OR, and the final neuron will compute OR or AND. All of which are linearly separable problem. I'm using the term linearly separable to mean you can find a set of weights which separates the positive examples for negative examples. And finding the set of weights is equivalent to finding a hyperplane which is drawn between the positive cluster and the negative cluster, and they are separated. Okay, because you can find a hyperplane separating positive from negative, and since hyperplane is expressed by a linear equation, such functions are called linearly separable functions, and is a linearly separable function. So any function which can be computed by a perceptron, a single neuron, which has a step function, it is called a linearly separable function. It's also called threshold function. So this network is adequate for computing XOR. But now do this experiment. Okay, start the XOR network with same values everywhere, same weight values everywhere. You will find that this XOR network doesn't converge. So what is the problem? This is called the symmetry breaking problem. Now let's take one solution of XOR, which is through x1 bar x2 and x1 x2 bar. Here we find that the weight values need to be different. So to compute x1 x2 bar, I need -1 and 1.5 as the weights emanating from x2, and -1 and 1.5 as the weights emanating from x1. And in the outermost layer, the input neurons, the input weights can be of same value, but the threshold has to be 0.5. The threshold is same as both the hidden layer neurons, 1, 1. So the parameters are different. Now, if the parameters are all same, then what will happen is that this network will not converge. Okay, so that is easy to understand. Why is it so? You see, the weight value by which the connection weight, the value by which the connection weights change, they are decided by eta into delta J into OI. So this particular weight, for example, W2, this will change by a quantity eta, learning rate, into delta at the output neuron multiplied by the activation coming from hidden layer neuron number 1. Okay. So we'll see that both these weights which are entering the output neuron, their value will continue to remain same. Okay. Because the change in weight is eta, which is same for both the connections, delta output, which is again same for both the connections, multiplied by OI, which is again same for both the hidden layer neurons. Because since the weights are same, since the weight values are same, the any input you impress on x1 and x2, they will send equal amount of input to the hidden layer neurons. And the hidden layer neurons have identical input output function. So they will be producing same activation at the output. So the amount by which the two output weights will change will remain same. Okay. So there is no way the two weights will become different. Okay. Now these two weights not being different maybe doesn't bother me. Let me examine what happens uh, to the weights below. Okay. So let me take the weights coming to x1 and x2. So I'm used to this being x1. So I'll make this x1. And this is x2. X2. Okay. And this is h1 and h2. So just verify that you are seeing the symmetry breaking slide. So let us see what will happen to the weight going from x1 to h1 and weight going from x1 to h2. Okay. So we claim that both these weights will continue to remain same. If they started out same, they will continue to remain same. Why so? The delta values here in h1 and h2 are same. Okay, the delta values are same. The reason is that delta at h1 is delta at output multiplied by the weight value, and delta at h2 is also delta at output multiplied by the weight value. So these two values are same. Now the delta at h2 and delta at h1 are same. So the amount by which weight from x1 to h1 will change will be eta, learning rate, into delta at h1 multiplied by input at x1. Similarly, the amount by which x1 to h2 will change will also be delta at h2, learning rate, into delta at h2 multiplied by the activation at x1. So both these quantities are same for both the connections here, from x1 to h1 and x1 to h2. So if they started out same, they will continue to be same. Let us take x2. The same argument shows that if the weights from x2 to h1 and h2 are same, they will continue to remain same. Okay. So this is called the symmetry problem, which needs to be broken. See, the weight from x1 to h2 and h1 have to be different when we compute XOR. Okay, when the network convergence, these two weights have to be different. One is -1, the other is 1.5. But if we started with, let's say, 1 and 1, the same increment will happen to these initial values, and they will continue to remain same. So this network will not compute XOR. Because to be able to compute XOR, we need the two weights to be different. So what will be the symptom? What will be the behavior of the network? What will happen is that it will always get stuck in a local minimum, and the error value will never come down below a quantity which is not acceptable to you, and the network will always misclassify the XOR input data. Okay, so this is the symmetry breaking problem. Now, why is it called symmetry? Again,
Sir,
papers and yeah, please.
so it will depend on the input also, right? So x1 and
Yes.
x2, if they are different, then we will have
No, we are
different.
considering the we are considering the connection going from x1. There are two connections going from x1. Okay,
Uh, yes. Sir. So
and
in the while changing input at delta x1
hmm.
will delta x1 will be similar as delta x2, but while changing the weights going from
No,
x1.
you're not getting the point. I am not bothered about delta x2 at all. I am bothered about. So next diagram will show you, which is why it is called symmetry breaking problem. You take x1 and x2 one below the other. Okay, instead of placing them side by side, you take x1 and x2 one below the other and draw a vertical line, okay, going through the output neuron. Okay, this is, let's say this is the what is this called, the the thing that is there in our back, the spinal column. So you can call this red line as the spinal column of the neural network. On two sides of these are the weights going from a single neuron. Okay, so these two diagrams are identical except for a rearrangement of their placement on the plane. So this is the x1 neuron and this is the x2 neuron. Now from x1, two weights are going to the two hidden layer neurons. Okay, so these two weights will continue remain same. The two weights going from x2 will continue to remain same. Okay, the two weights going from h1 and h2 will continue to remain same. That is the point.
Oh, yes, sir. Got it.
Got it? Yeah. So we're not comparing x1 and x2. We are comparing the two weights going out of x1. And this diagram, unfortunately, is not shown in any research paper or textbook. Okay, my slides makes it clear why it is a symmetry problem and why this needs to be broken. So the exercise for you is the next statement. Find the weakest condition for symmetry breaking. It is not the case that when only all weights are equal, the network faces a symmetry problem. No. So all you need is the symmetrical weights should be same around the spinal column of the neural network. Okay. So only these two weights need to remain same. We do not worry about a neuron to neuron comparison. No. From the same neuron going to the next layer, what is the value of the weights? That is what is of concern. Now you can have any number of hidden layer neurons, any number of hidden layers, any number of neurons in the output layer. So that would be the most general condition. You have to condition. Common misconception for students to compare weights going between x1 and x2. No, it is only the weights going from single neuron to the next layer, which is of importance to us. Okay, so this is the symmetry breaking problem. So with respect to backpropagation, we discussed a number of important things. The linear neurons, the mathematics, I'll have to fix a bit. There are a few mistakes with the suffixes, so that I'll do. Now, the first point was that if we have linear input-output relation for every neuron, any hidden layer is of no use. Okay, any neural network with any number of hidden layer neurons is collapsible to a input layer, output layer neural network. Okay, so you do not gain any additional power because of the linearity of the input-output function. The next point, and that the reason is that a neuron with linear input-output relation is also not able to compute XOR. Okay, that can be shown by setting up inequalities, and that set of inequalities will be internally inconsistent. The next point we discussed was local minimum. Backpropagation is a greedy algorithm. So whenever you get stuck at a local minimum, there is no way you can come out of that local minimum and go to the global minimum iteratively. You will have to restart the system, reinitialize, restart. So you'll have to shake the system out of this local minimum. Now there is a variation in the neural network called the Boltzmann machine. So the Boltzmann machine, what it does is that, Jyotsna, can you please add this slide? The Boltzmann machine, what does is that it can shake the operating point out of the local minimum because of the following reason. In backpropagation, we always take the weight, increase the weight or decrease the weight, obeying the law of negative gradient. Okay, so if the so every time the error reduces, you increase or decrease so that the error reduces. That is the gradient descent law. Now I introduce a probabilistic operation here. So I will take a step which will reduce the error, but I'll have a small probability of increasing the error also. So instead of always decreasing or increasing or decreasing the weight instructed by the gradient descent law, I will toss a coin, okay, and if it is head, then I will follow the gradient descent rule. If it is tail, then I'll give a small increase in the weight. Okay, so that is the foundation of the Boltzmann machine, which also came early, and that actually can take the operating point out of the local minimum. And very interesting lemma theorems observations can be made if the gradient descent um, if the change in weight as per gradient descent is altered by this kind of random weight change. You obey the gradient descent rule. Okay, the change in weight will be eta into delta j into oi. That you do. But you also toss a coin, and with a probability which you can control, okay, with a probability which you can control, you can increase the error also. Okay, change the weight in the opposite direction, not increase or decrease. If increase is demanded, you decrease it. If decrease is demanded, you increase it with a small probability. So this is an example of a randomized algorithm. Okay, and that can take this system out of local minimum and some probability they can get. Probability algorithm has a possibility of taking the system to the global minimum also. So this is a local minimum problem. The next important variation on backpropagation we discussed was momentum factor. In momentum factor, we change the weight by eta into delta j into oi, which is as per gradient descent rule. But I add also a proportion of the previous weight change in the previous iteration. That is done by introducing a momentum factor beta. So beta into delta wji at the n-1th iteration is added to eta delta j oi, which is the weight change at the nth iteration. So this is called the momentum factor, and the effect of that is that if your weight change is of same sign, then the combined weight change becomes larger than eta into delta j into oi. So you take bigger steps towards the minimum. But close to minimum, since the weight change is likely to have sign change also because you are close to the minimum, so there will be oscillations. That is dampened because the two subsequent weight changes, consecutive weight changes are of different sign. So that has the effect of reducing the weight change value. That is like a damping effect. So momentum factor has both these advantages. It accelerates the movement towards local minimum, but close to local minimum or close to minimum, it dampens oscillation. So one might ask, why not go on increasing the momentum factor, give it large values? But what happens is that you can expand this into a geometric series, 1 plus beta square plus beta cube, etc. And that after some time dominates eta delta j oi if beta is large. If beta is close to 1, it completely overshadows, the momentum factor completely overshadows the gradient descent rule. And the algorithm no longer remains a backpropagation algorithm. Okay, so this will be controlled by the initial weight value, initial weight change, and that completely determines how the weight change happens. So it is instructive for you to sit down and expand the momentum factor and see, expand it over iteration and see how it can dominate the gradient descent rule. Okay, so this is instructive for you. Next thing we discussed was the vanishing and exploding gradient problem that can be understood by a stack of hidden layer neurons. Stack of hidden layer neurons. Deep neural networks are many a number of neurons and many number of layers, and we saw that even very reasonable number of neurons and layers, 10 neurons for 10 layers, every layer containing 10 neurons, so 100 neurons, 100 hidden layer neurons. That itself gives rise to 10 to the power 10. 10 to the power 10 addition terms when we compute delta x1. And before that layer, it will be slightly less than that, but still a very large number of computations. So you can see this is really a very hard computation situation and not really acceptable. Therefore, you must cut out the computation of gradient delta at some point of time, which is what LSTMs do, long and short term memory. Why is it called long? Why is it called short? Why is it called memory? Okay, all these you need to understand. Not that always the names make sense, but in this case the name makes sense. Long and short, long and short. Okay, because one of the contributing factors is product of weights. Another contributing factor is the exponential number of addition terms. Okay, so both are a botheration, and therefore you have to deal with them. By the way, I'll be, as I've mentioned many times in the class, next semester I'll be teaching this course called Deep Neural Networks, Deep Learning for Natural Language Processing. So there we'll see that this vanishing and exploding gradient needs to be tackled. We don't worry because we have LSTM, by LSTM, etc. at our disposal. But long sentences are common. You can easily have 30 words long sentence. 30-word long sentence would mean 30 stages of computation, which is equivalent to 30 layers. 30 layers. Okay, and each neurons also is okay. So NLP can get into exponential situations for computation, and there would be explosion of terms very easily, and each individual term can have vanishing value because of the product of weights. The product of weights should be clear to you. You can see here W12 W11 comma 1 multiplies W21 comma 11 and so on. So this is very common. And just one sec. Okay. So product of weights and exponential number of addition terms. And then we discussed symmetry breaking. We understood that the weights around the spinal column of the neural network cannot be same. So this is the complete. This is the complete. I'll not say complete. This is the useful discussion on backpropagation and feed-forward network. If you have followed this discussion so far, I would say that you have got the essence of the feed-forward network, which is trained by a backpropagation algorithm. Okay, and that concept is replicated in softmax network and even recurrent neural network, which we are going to see. So feed-forward network with backpropagation is a foundational discussion which needs to be understood carefully. Now we would like to start recurrent neural network, and we would like to see next week the application of feed-forward network to backpropagation to natural language processing. In particular, maybe we can take one of the problems in natural language processing like sentiment analysis, text classification, or even a foundational task like dependency parsing. So when we do dependency parsing, we have to decide what is the head. Okay, so let us see if we have. No, I don't think I have the dependency parse diagram here. Okay, but for dependency parse diagram, the first step is finding the main verb of the sentence. So Jyotsna, can you please add a slide? So the sentence has passed through part of speech tagging. So all the verbs, nouns have been identified. And if there are multiple verbs, then which verb is the main verb, where the root arrow will enter. So if the root arrow enters a node, that is the indication that that is the main verb, and root is the head, whole sentence is the modifier for the head. Then recursively, we find heads and modifiers in the subparts of the clauses and phrases of the sentence. So after that, it is a question of finding out uh, the heads and modifiers in the whole sentence. So head and modifier decision is a classification decision. I come to any position and I ask, should it be a modifier or should it be a head? Okay, if it is a modifier, then this modifier is modifier for which head? So that is the decision we keep on taking at every position. This is called the transition-based dependency parsing. So transition-based dependency parsing is like a classification problem, and therefore it is amenable to a neural network-based computation. So if we had more time, I would have asked you to implement as an assignment the dependency parsing using deep neural network. But those of you who are curious might want to do this anyway. Train a feed-forward neural network for doing dependency parsing. There are umpteen number of papers. Now we have little more time before we can take up question answering. So I'd like to introduce recurrent neural network. And recurrent neural networks are mainly used in sequence processing. So natural language processing is a very nice example of sequence processing. In computer vision also sequence processing can come if we have to do scene understanding. Okay, in movies, for example, we know there are frames after frames after frames which come, and that depicts the story of the movie. Okay, we also said that if we have a vigilance surveillance camera, which is watching out for any kind of terrorist activity, then a person bending, picking up something, doing something with the picked up object, those scenes are suspect scenes. And the surveillance system is trained to watch out for these kind of signals and raise a flag, raise an alarm. So, but not all bending and picking up objects activity is an example of terrorist activity. No, so it is not. So people bend down umpteen number of times, pick up objects. Not most of them are not terrorist activities. So so the surveillance system must have been trained on enormous amount of data, and the classification decision has to be really fine-grained and accurate to detect that there is something unusual in this activity of bending, picking up an object and doing something with the object. So this is a sequence of 3 frames which the machine is examining and giving decision on. Sequence processing comes in autonomous vehicles also. When a car is moving on highway or on some road, then the frame after frame after frame, there is change of scene, and you have to take an action for each scene. But natural language processing has a natural sequence processing situation. I'm doing part of speech tagging. You have done part of speech tagging assignment. At every position, there is a word. And before the word, you have done one part of speech tag assignment. So that previous state, which is the part of speech, the current word, and other properties in the current position, the word suffix, for example, the number of characters in that word, etc., help you make a decision. You have done this in chunking. Okay, in chunking, the problem was much simpler. There were only 2 classes, B and I. And with B and I, and with the previous B or I in the previous position, you have done the assign B or I at the current position. So this is a very natural sequence circle here, and there is a weight coming back to the block itself. This is the feedback weight, and V is the weight for the output layer, and the input is the input vector X, which is going to this neural block through the weight U. So U is the weight of the input vector to hidden block, and then from hidden to output the weight is V, and this W is the weight vector coming back to the hidden block. Okay, so U, V, and W are the weight values which decide the computation. Now, because of this feedback connection, there is a recurrent computation going on in the network. Okay, it can go on infinitely. And for every input, it is xt minus 1, xt, xt plus 1, t minus 1 at step, t at step, and t plus 1 at step. So this is how the computation proceeds, and it is like unfolding this neural network over time. And this becomes equivalent to a feed-forward neural network. Okay, this becomes equivalent to a feed-forward network, as we'll see. So at this point of time, I'll stop. I'll talk about usage of feed-forward network to some NLP problem in the next week, and also the sequential processing through RNN will be the discussion going forward. Okay, what questions are there, Diptesh?
Uh, I believe there's only one question, sir, and Parth has asked that in
Yeah.
probabilistic setting, we
Hmm.
can avoid the local minima, but due to the same reason, we
Hmm.
won't be able to converge at global minima as well, right?
Hmm. I don't think I understand the question. Once again, please.
Parth usually unmutes himself and talks in
Uh,
these cases.
Yeah.
Sir, I wanted to ask that means since we are avoiding local minima by sometimes just not going the reverse direction, we
Hmm.
will do that same in global while converging at global minima also, right?
Hmm. Hmm. Yeah.
So it might be possible that we won't converge at global minima because we will
Yeah. 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 Hmm. No, no. So you see, you are doing a randomized algorithm. So you are tossing a coin and deciding if you should change the weight, decreasing or increasing it. Hmm. So now it is possible that you have come to global minimum and you do not recognize that this is the global minimum. It is impossible to distinguish a local minimum from global minimum. Okay. All you can do is that you set a make my error below 0.1 or 0.01. Okay, and the moment you achieve that, you stop the computation and you do not worry about local minimum or global minimum. Local or global minimum or local minimum comes into picture when the network doesn't seem to reduce error at all. So there you have to suspect the network might have been saturated, or it has reached a local minimum, or the number of neurons in the hidden layer are not adequate, or number of layers itself is not adequate. Yeah, you're right that
okay.
you can also miss the global minimum. You reach it and you come out of this because of random operation.
Yes, sir. Thank you.
Sir, Kaveri is asking
Hmm.
that RNN uses the same W values, I believe it's weight value for
Yes,
each
yes,
input.
yes.
Do they suffer from the symmetry breaking problem?
Ah, okay. So you see this diagram, if you see time step 0, time step 1, time step 2, symmetry breaking problem is only for weights coming out from a single neuron, okay, from one particular neuron going to the next layer, okay. So so since the neural network is unfolding itself, okay, the same weights are getting repeated at every time step. These weight values are being compared layer across layers, not from one neuron to many neurons in the next layer. So the weights going from one neuron to all the neurons to the next layer is our concern, not layer to layer weight comparison. Okay, so symmetry breaking that way doesn't really affect RN.
Sir, the chat box does not have any other questions, but may I please ask you to clarify something regarding the medicine? A very first question.
Aha, yes, yes, yeah.
So that communicate being a STEM, some people have constantly been asking me whether commune can also be a STEM.
No.
But
Hmm.
in my opinion, commune cannot be a STEM because the Costager will, let us say, act as a module. And
Hmm.
I'm just trying to validate my own opinion. So this is probably just for the benefit of our own discussion.
Hmm.
So the Costager will have to take forward communicate as a STEM because then again it's just a module in the whole NLP pipeline, right?
Hmm.
And when we are looking at the word uncommunicativeness, we are
Hmm.
basically trying to, that word semantically is trying to refer to something being non-communicative.
Hmm.
So with that logic, I believe, and given the fact that this question being is being answered by a human and not a statistical Costager, communicate seems to be the logical step.
No, so it is not really logic or it is not really computation. It is what is linguistics telling us. Okay,
Okay.
so the communicat, COMMUNICAT, communicat
Yes.
is recognized by Latin as a
Okay.
stem. Okay, and
Right.
all these languages descended from Latin. So
That
remember
is
that NLP is not only computation. NLP is quite
that's
a lot of linguistics also. Okay, cognitive science, linguistics, physics, philosophy, and so on.
right.
So you need to be both scholarly and computationally proficient. Okay, the scholarly part comes from non-computer science inputs, which are linguistics, cognitive science, physics, entropy, philosophy, and even sociology, humanities, and so on. It's a very vast landscape,
Right.
very vast panorama. Okay, so inputs come from many sides and it is shape. So suppose and the forward striker finally strikes a goal. Okay,
Right.
putting the goal past the goalkeeper into the net.
Right.
But that is only the final step. Okay, before that there is a whole planning
Of
which is
course.
done by the
Midfielders
midfielders,
and
okay, and
right.
defenders. So
Right.
they create this situation where the striker finally puts the ball into the net.
Right.
In NLP also the computational steps comes at the end, okay, by
Correct.
implementing the system, doing an analysis, getting accuracy figures, F score, precision recall, etc. But there is a huge amount of planning with inputs from multiple disciplines
Right.
which goes into creating an NLP system. Okay, people might say this is not the case in deep learning situation where there are end-to-end systems and you don't have to bother. You just give huge amount of data to a machine learning module and the result will come. This works at many places, but the point is that data is really short in supply for many problems and many languages. Okay,
And
so
even
there
that data has to be labeled and annotated by
also
manually by
also
lexicographers and linguists. So
also
again, that goes
also
to background knowledge.
right. So